you find yourself getting into trouble with any of the calculus, let me know so I can at least set you up with some kind of, I mean, I have a whole calculus 2 class that I recorded last year that's already up online because I taught asynchronously in the winter last year. So that's already there. I can recommend sections from the book. You probably can go get help with that stuff in the tutoring labs if you need to. Don't tell them you're there for 304 or they'll laugh at you. But if you have trouble with calculus, you can certainly get those questions answered. Is there anything I can answer? All right, keep it up. I think you guys are doing a good job in here. Yeah, we'll just keep going.
Will you post the solution?
Oh yeah, solutions to everything will be posted like prior to the end of the class for sure. I will have stuff posted. I'm sure I have a backlog I'm chipping away at. I will get solutions to this posted when I can. Yeah. Yeah, I don't give like I always give exams back and give full solutions. Okay, so last time we were in section 3.3 and we were talking about vector fields. Sort of an introduction to vector fields. And one of the things that we looked at when we looked at vector fields was, well, first off, what is a vector field and how do you get one? So a vector field is a function f that takes a domain in some kind of Rn into Rn. And remember, we thought about that as a function that takes in a vector and assigns it a vector, or takes in a point and assigns it a vector. So if we go from R3 to R3 or R2 to R2, we're thinking every point gets a vector attached to it. This would be an example of a vector field. I probably wouldn't have an arrow pointing off like that if it was going to be continuous. Right? This is an example of a vector field. And the easiest way to get a vector field is you start with what's called a potential function, f, which takes, say, in Rn into R. So this is called a scalar field. And then you take its gradient. So capital F of x is defined to be the gradient of little f evaluated at x. This is a gradient field. Okay. That was the easiest kind of vector field that we studied, or that you can define. And remember, the idea here is that if you have a level curve, so this is a place where f is constant, then the gradient field is always pointing perpendicular to that. So on. So this is a level curve. And the gradient field is perpendicular to the level curve. Gradient f of x is perpendicular to the level curve. Okay. And the last, very, very last thing that we talked about last time were flow lines, where I discovered that beginning differential equations is not a prerequisite for this class. So we're just going to pretend that first order differential equations are not a thing that exists. I'm going to write down how you get a flow line to a field. But I just want you to have the picture in mind so that when we start working, when I give you demos using the computer on this, you understand what the flow lines are actually doing. Okay. So the idea was, if you have some level curves, and attached to that you have, or you pick some point in space, that the flow lines are the lines that the tangent vector was equal to the gradient vector. The idea here being, if this is the gradient to the function, and this was the gradient to the function, that the velocity vector of the path was equal to the gradient vector that came from the vector field. Okay. And then, like I said, I discovered that to compute flow lines, which involves solving this equation, x prime of t, that is the velocity vector for the path, is equal to the gradient vector of f at that point in the path. That's a differential equation, which we technically don't have the tools to solve. So what do you do to get those? You stab it in a computer and click a button. And the lines it draws for you are the sort of flow lines for the vector field you're looking at. Okay. So you will learn how to do this. This is a system of first order differential equations. It's important to be able to work with those things. If you haven't done differential equations yet, I'm not going to make you do it. I just want to point out that that's how you get those. And you don't even have to compute those, just if you can interpret this is a velocity vector, and that's the gradient vector for a vector field or a force field. Okay. Okay, that was what we did last time. So what are we going to do today? We're going to define some fancy derivatives. I'm going to start with an operator, kind of a weird one, called the del operator. This is 3.4. This is the del operator. Okay, so here's how the del operator is defined. Symbol. Does anybody actually know the name of that symbol? It's not del. Nabla, yeah, or nabla. It's an odd name for a symbol, but if you were working in LaTeX for whatever reason, this is /nabla.
How do you spell nabla?
N-A-B-L-A. All right, so it's a vector, and the vector, it's kind of a vector because it's just a vector that has some partial derivatives living inside of it. That's not supposed to be 2x, 2y, and 2z. These are partial derivative operators. Okay. The other way you think about this is d by dxi plus d by dyj plus d by dz k. So it's a function, but it's a function that we've somehow structured to be a vector. Okay, so it's weird. Since it's a vector, we're actually going to use all different kinds of vector products on this thing. Notice that this is a three-dimensional vector, right? So we're going to try to define derivative. I mean, it's a derivative operator because it's built out of derivatives. So we're going to use all three kinds of multiplication of vectors to make new operators. We're going to use scalar multiplication. We're going to use the dot product. And we're going to use the cross product to make new things. And we're going to have to be a little bit careful about how we define the functions we do this with, because these are going to have to go along with the structure that we've set up. When I take a dot product, I've got to take a dot product of vectors. When I take a cross product, I have to have a cross product of vectors. But that one, we've already seen that one. I mean, del F, the way you say this is del F. Del F is the gradient.
Why are we doing this?
Why?
Yeah, why?
Why are we doing this?
Yeah.
So we're doing this because this is an excellent question. So you might think, okay, so am I just like randomly, hey, my math professor decided we're going to invent this thing and just slap it around on some symbols and see what happens. It turns out that these quantities measure fundamental characteristics of the way vector fields act. So this guy right here is going to turn out to be the gradient of a scalar field. So you put in a scalar field and you get out its gradient field. This one is going to turn out to be equal to the divergence. And divergence measures how much fluid is moving in or out of a certain space in a vector field. So this measures fluid flow. This one is called curl, which measures the local rotation of a vector field. And all three of these quantities have deep physical importance. So these three derivatives study three different ways that these functions move. Okay. Yep.
When you say del dot F, what does it mean? Is it like
I'm going to tell you. I'm going to tell you. I promise. I promise. I haven't. I'm sort of just setting up where we're going. I'm not telling you how we do it yet. Okay. I'm going to motivate this by writing this symbol down. We've been writing this down, and every time we write this down, we've been writing down df dx, df dy, df dz. But this way of thinking about it would be it's d by dx, d by dy, d by dv applied to f, right? It's like you're scalar multiplying this scalar function f into the del operator to get that. And what does this do? What sort of object do you put in and what sort of object do you get out? Well, the gradient of grad f, how are we writing this? The gradient takes in a scalar function and produces a vector function. So the gradient takes a scalar function to a vector function. It turns potentials, right? It turns potentials into forces, if you like, right? You take in level curves, you get out the flow lines. The gradient describes directions of greatest change. Okay, that's our motivating example for why. And so what we're hoping is that, like, I mean, I'm setting it up like I'm pretending like we're discovering something. I already know these have meaning, so we're going to define these because these are meaningful quantities, very interesting meaningful quantities. So now it's a great question. What exactly do I mean by this? That just looks like nonsense. So suppose that f is equal to f1 comma f2 comma f3. So f has to be a vector field, right? F is going to take R3 into R3. It takes in 3 variables, it spits out 3 functions. So I'll write this out in longhand once so you can see what I mean. What does a 3-dimensional vector field look like? If f takes in a domain in R3 and spits out a vector in R3, then that means that f of x, y, z is equal to f1 of x, y, z, comma, f2 of x, y, z, comma, f3 of x, y, z. Make sense? You take in 3 variables, you spit out 3 variables. These things are called the component functions. So this takes in a vector that's 3-dimensional and it spits out a vector that's 3-dimensional. So this is what you mean by a vector field in R3. So what does this mean? This is equal to d by dx, d by dy, d by dz, dotted with f1, f2, f3. I just compute it like a regular vector dot product. It looks weird, but this is df1 dx plus df2 dy plus df3 dz. This times, this times this, this times this, this times this, and add them all up. That's how you do a dot product, right? Dot product 2 vectors, you add them, you multiply and then add. And this quantity right here is called the divergence of f. So what this measures is a little more subtle than what the gradient measures. I guess the first thing we should note here is this operation took in a vector field and produced a scalar. So this started with a vector as the input, but what came out in the end was a scalar. So the divergence is a scalar field. Divergence takes a vector and turns it into a scalar number. So what does it measure? And we're going to be more clear about this once we get Stokes' theorem. I'm going to do my best here. So no physicists or people taking fluid dynamics get to laugh at this explanation. I'm going to do the best I can. Okay, so what does this actually measure? I should say that this is a scalar. Imagine that you've got some vector field. Okay, pick a point. Draw a little cube around that point. there you go. There's a cube sitting in river or whatever, right? What the divergence is measuring is something like the net mass flow in this square. So it takes all of the vector field leaving and all of the vector field entering, and it sort of adds it up into an average amount, like a net flow in and out. So this, I mean, how much net flow would be in and out in a constant field like this? It better be zero, right? The amount of fluid in is equal to the amount of fluid out. So this sort of picture would be net flow, like something like net mass flow or something like that, is equal to zero. Again, this will be made much more concrete once we get the integral theories to go along with it. The idea is, if it turns out to be the case that the divergence of a vector field is equal to zero everywhere, so that is every single point inside the space, you draw this little square and the same amount of water goes in and out. That's what we mean by an incompressible vector field. Incompressible means every single point has the same amount of fluid coming in as leaves. If you think about the analogy with water there, what you're saying is there's nothing where you can crush a bunch of mass in and have less mass come out the other side. That would be you're compressing things when you do that. One of the great assumptions of fluid dynamics is that water doesn't compress, which is mostly true, right? So these sort of fields represent fluid flow, like incompressible fluids. So divergence zero means fluid in is equal to fluid out, as opposed to non-zero divergence fields, where you might get stuff that looks like this. I think I talked about this last time. There's a vector field where you have a whole lot of vector field arrows pointing into a dot. If you drew a little square around this, it sure looks like a whole lot of fluid is coming in and nothing is leaving. So this would be an example of divergence of F not equal to zero at that point. Like water won't do that. Yep.
Why is square not circle?
I mean, you can use circles. Yeah, I mean, the reason that you do it with squares is because squares give you ways. We'll find when we start doing the theory of integration that what squares give you is a coordinate system where you can take dot products in this direction, and this direction, which lets you actually compute how much of the vector field is flowing through each of the faces. So squares are the normal thing, because if I set up a flat plane and I say how much of the vector field is flowing through it, that's an easy question to compute once we have the integral theory. That's called flux, right? So that's why I'm drawing the squares instead of circles. You can do the theory with circles too. It's just more theoretical and less computational. Okay, so divergence basically measures, are things flowing through, or are they compressing, or are they expanding, right? That's what divergence measures. At a given point, do we have steady flow through? Are we taking in more mass than we're letting out, or are we emitting more mass than we're letting in? Okay. So that's divergence. It's the bad word. So okay, so that was the gradient took a scalar field to a vector field, and the divergence took a vector field to a scalar field. So we got one more to go. How are we going to take a vector field to a vector field? Well, we can compute this thing. This is called the curl of F. And the way you compute it is by doing the determinant of this matrix. Now, please, for the love of God, do not memorize this. Like, this is fine. You should memorize this. Don't memorize the actual computational formula for curl. So, we're going to put what? F1 right here, F2 right here, and F3 right here. Okay. Now I'm going to write this out one time. You don't have to. I times df3 dy. Do I actually have to do this? Fine. df2 minus j times df1 dx. No, df3 dx minus df1 dt plus k times df3 dx minus df2 y. Now you might think, okay, how could that possibly measure anything? Right. So don't memorize this. Don't memorize that. When you ever have to compute curl, you just work with this directly. Okay, there's no reason to memorize this. Just memorize that it's the cross product of the function with the del operators. The way you say this one is del cross f. Okay, now curl is actually another interesting quantity because curl doesn't measure this. I mean, we're calling it curl, so you must imagine that somehow twisting or rotating is going to be involved in this picture somehow. So what curl measures is the local tendency of a vector field to rotate around an axis. Yep. Did I make a mistake?
Yeah.
Probably. It's df 2 dx df 1 dy. My bad. This is why you shouldn't memorize it. You should just do it yourself. Okay, so what does all this nonsense measure? Well, the first thing to notice is that it's a vector. And if your life in this class has taught you anything, it's that like when we have vector quantities, both the magnitude and the direction tell us something. So what we're going to learn after we get a theory of integration is that curl measures local tendency to rotate. So curl measures local tendency to rotate. And I'm gonna draw a picture to describe what I mean by the word local here. So here's an example of a vector field with no curl. So if you have a vector field and in that vector field you draw some sort of flow line, right? This is a flow line in a vector field and it's curled around like this. And you drop, say, a toothpick or a stick onto this so that this was things on here were traveling in a path like this, right? If you dropped a stick onto this and everywhere on the path, the stick had the same orientation. It never rotated, even though it was traveling around the path. So the stick is kind of traveling like this, right? It's not changing its orientation. It's moving in space, but it's never twisting like this. This would be a no curl vector field. So no local rotation means this never rotated. It slid in the vector field, but it never twisted around in a circle like this, right? So this would be no curl. On the other hand, if you drew the same picture, with the same sort of closed flow line, but now as the stick travels, it rotates around in different orientations. Let's see, down, this way, this way, this way. So now it's like it's spinning as it goes around, right? You can see it rotating as it turns. This tendency to rotate as it slides is what we mean by local curl. Okay, so this would have, I guess, no curl, yes curl. And we're going to do a deeper analysis of what curl and divergence and gradient mean when we get the Green's and Stokes theorem later. For now, what I want you to imagine is if you were in three-dimensional space, the magnitude of this vector tells you how much rotation you have at a given point. And the direction of this vector tells you the axis of that rotation. So the magnitude of curl is the amount of rotation, and the direction is the axis, which is pretty useful, right? To say like, oh, locally, this is the axis that it's rotating around, right? So like if I think locally, this is where things are spinning. So when you're studying fluids or any sort of like airflow, yep.
So, sorry, back to the stick. Is
Sure.
it as if like the stick was just stuck on the
Yeah, exactly, right? So it's like what you imagine here is there's some axis that it's trapped on, but it never spins around that axis. It's just stuck there. So whereas here, the way I've drawn it, the axis never moves, but around that axis, the stick is twisting, right? Another way of looking at it is if you could somehow fix it at that point, and you spun the axis so that it was the right direction, then the stick would spin in the medium like that, right? Right. So curl-free fields are of supreme importance in physics. So these are called irrotational fields, and those turn out to be those that are conservative. The conservative vector fields, which are like the core of physics, are fields that have no curl. Okay, so we got a couple of more things we want to say about that. At this point, this is just going to look like computational mathematics. I'm trying to hook it up with why we're trying to study this. Ultimately, what these things will be used for is to study vector fields that so we're gonna study things like how much fluid is flowing across a surface. If I was in a pipe and I put a membrane or a mesh in the pipe and I wanted to compute how much fluid went through that, I would use this theory plus integration to find that out. If I was trying to figure out the flux, the magnetic flux through some surface in space, and the shape was complicated, I would use integration theory stuck together with these ideas to do that. So we're going to use this to build a theory of integration that will let us study big, complicated physical systems. Okay. So here's a couple of cute theorems. It's I'm going to call these cute because I'm a mathematician. I'm allowed to do that. So here's some classic. I'm going to call these classic do-it-yourself theorem. Oh yeah, do it yourself. DIY. Whatever, man. I've been going too long. DI. Yeah, do yourself in theorem. Okay, so classic do it yourself theorem. So first one is let F. You know what? I'm not even going to give you the hypothesis. I'm just going to tell you. This is the way these usually be written on an exam. Curl of the gradient of F is 0. As a computational proof. You can prove that. Here you have to assume in order for this to make sense that F is, I think F has to be C2. Twice continuously differentiable. And I mean, this makes sense. Let's make sure this makes sense. So F is a scalar valued function. Its gradient is a vector valued function. Its curl is a vector valued function. So we're calling this an irrotational field. Curl 0. Irrotational. And likewise, the divergence of the curl is equal to 0. Let's make sure that makes sense. Curl takes a vector to a vector. Divergence turns into a scalar. So this makes sense. So two of these operators applied in a row. If you wanted in the classical version, you'd write this. Del cross del F is 0. There you go. You can level up the way, you want to look like a super nerd. You start writing like this. Divergence was del dot del cross F. There you go. So in symbols and in names of the operations. So you should at least try these. You can try to show these. Not hard, just a computation. These have physical meaning, like I said, that we'll get to when we talk about the Stokes theorem. Okay, so now we need to pause with this kind of differentiation. I mean, the reason we're doing this now is because we're trying to settle the last bits that we have to do with the approximation of things or study of things with derivatives. We have one more big idea left to go with that. This stuff is going to come back in a big way when we start building our theory of integration. Okay? So for now, you should think of these as in the same way, as unsatisfying as it is. In Calculus 1, every time you got a bunch of new derivative techniques, you had to go do a bunch of derivatives, right? Like, oh, here's the product rule, now go compute some products. Oh, here's the chain rule, go compute some derivatives. Maybe find some tangent lines, right? This is the same kind of thing at this point. You've got 3 new types of derivatives of these functions. You got to compute some and get comfortable with how they work so that when we get to the point where we have to use these in the theory, it's going to be like second nature. Okay. And I mean, it's unsatisfying, but this is the way that the book is set up. We have to go into actually my favorite area of this entire thing, which is Taylor series. That's next. Okay, so there are questions about, maybe let me compute an example here and then we'll leave this. Right. So let's get maybe one that's not too gnarly. All right, so let's let f equal to x squared y minus 2xz x plus y minus z. What operations are even sensible with this? How can I act on this with the del operator? Which one? If it's a vector field, so what can I hit it with? Can I take its gradient?
Yeah.
Gradient. Gradient is a scalar multiplication, right? Del times f. That's not a scalar field, so that's not going to be defined, right? I can use the vector operations on this. If I did this, yeah. Am I computing with this? But which property of a vector field am I uncovering with this? Is it curl, grad, or div? It's div, right? This is the divergence of f. And it is equal to d by dx applied to this, plus d by dy applied to this, plus d by dz applied to this. So this is the divergence of this. Is there a point you can think of with divergence 0? Such as? So what's that? Xy equals 1/2. All right, there you go. X is equal to 1. Y equals 1/2. There's one that works, right? You plug those in, you get 1 minus 1. Is this vector field incompressible? Is F incompressible? Well, incompressible means that the divergence of F is 0 everywhere. Is that true? No, right? I didn't give you a domain, so you have to assume it's defined on all x's and y's. So it's not I mean, if that says incomprehensible, probably that's. Yeah, is F incompressible means is the divergence 0. So if in your mind you think, okay, that can't possibly represent water in any sort of meaningful way. So the answer is no. Divergence is not 0 everywhere, so this is not an incompressible field. What else could I do to it? Well, I can hit it with the curl. I, j, k, d by dx, d by dy, d by dz, squared y minus 2xz. This is the sort of exercise you do if you're sitting around and you just decide, you know what, I really want to like torture myself for a while with cross products. It looks like 2x, 2y, 2z, but I mean partial sub x, partial sub y, partial sub z. I'm not trying to confuse you. I'm trying to introduce you to all the different ways this notation shows up. Yep.
So we may speak of like a vector field and you're exploring different stuff.
That's right. Yeah, these are all quantities used to explore this vector field. So if I gave you this vector field, I might ask, what's the divergence at every point in that vector field? This is how you measure it. Yeah. So this is the question. What is the divergence of the field? This is not incompressible because different values. I mean, if you start plugging numbers in, you're going to get actual values here. Physicists in the room might be irritated at the fact I haven't put units on everything, but deal with it. So in theory, you can put units on this and make this physically meaningful.
What about that one?
This is the curl of F, is what we're measuring when we write this one down. So this measures like fluid in versus fluid out at a point. And this one is measuring how much rotation is happening at any given point and what direction is it happening in. Okay. So to compute this one, you've got to compute. What is d by dy of this? It is x, that's 1. And d by dz of this guy is minus 2x, so it's 1 plus 2x there. Minus j times d by dx of this, which is 1, minus d by dz of this, which is 0, plus a times d by dx of this guy, which is minus 2z, and d by dy of this guy, which is x squared. All right. Now I don't want to write down, I mean, I could if I wanted to, I could write down, you know, d by dy of this minus d by dz of this, and then do the computation. But like that just gets, it's going to take a lot to do that. So if you know what you're doing with these determinants, and you should, because the point is to do enough of these that you never get confused by it. You just compute them directly. Now, maybe I made a mistake. Let's see. That's 1, that's minus 2x. The reason I put a plus here is because you subtract the negative 2x. Minus j times 1 and 0. And then for k, it's this, which is minus 2z, minus this, which is x squared. Yeah, I think I got it right. Okay, so this quantity, curl f, like this, 1 plus 2x, minus 1, minus 2z, minus x squared. Is that ever equal to 0? So there are no points in this vector field in which there's no rotation happening. Not a single place where this thing has a calm spot, a non-rotational spot. So this is the vector that measures axis of rotation. So this would not be irrotational. Because that requires that the curl F is equal to 0 everywhere. So I guess you would say rotational. And what we'll learn, incompressible and irrotational. So that's just definitions. Because we can put physical meaning on this quantity. The physical meaning that we described with this being 0 everywhere, which is the same as saying the divergence of F is equal to 0 everywhere, which is the same thing as saying that the field, every spot in space has the same amount of mass coming in as leaving. We call this incompressible. Because really the reason we call this incompressible is because these are vector fields that act like water does under motion. Water is an incompressible fluid. You can't squeeze it, right? It doesn't do that. So there's characteristics that water doesn't have. So these are the sort of water-like vector fields. Then we had another family of vector fields that look like curl F is equal to 0. So if the curl of F is equal to 0 everywhere, which was the same as saying that this is 0 everywhere. Well, here what we're saying is no rotation is happening anywhere in the field. So there's no local rotation. In the sense that curl can be said to measure how things rotate, which you shouldn't necessarily even believe yet because I haven't proved it. I'm just asserting that. But this is what curl does, right? Curl measures rotation. If I say the curl is 0 everywhere, it means there's no local rotation, and we call that irrotational. And then I hinted that eventually these are going to be called conservative. Because these are going to be the things that have integrals. Yep.
So for the curl F to be 0, each component would just be a 0, right?
That's right. It's the 0. Yeah, this is a 0 vector. Yep. Yeah, because since curl is a vector value function, it definitely has to be 0, 0, 0. Yep.
Can these be irrotational or incompressible at a certain point only? Or is that
You could say, you could refer to like things as being locally curl 0 or locally irrotational, but if like usually you would say you wouldn't use local. I mean, you can. In some problems they do this, right? Like there might be places where things look incompressible or where things look irrotational. In application problems, normally what that has to do with like what the scope that you're looking at is, right? Where you set the parameters of the system you're studying. So normally we use these words to mean globally. Like globally, there's something is irrotational means there's no rotation anywhere. And the reason we want that is because if something is irrotational, it's going to turn out to be integrable. I can undo it. Right? Yep.
Since we don't know how to do the rate,
Oh, I didn't say you didn't, what I said was, you need to know how to do the operation, but you shouldn't memorize this line, right? There are people out here that try to actually memorize the formula you get out of this. You do need to know this and how to do it. But if somebody actually sat down and did, that the curl of f was equal to dx df1, dy df3 minus dz df2, and just memorize that gigantic long equation instead, that's a waste of time. Right? If you remember what a cross product is, and you know what the del operator is, you can reconstruct what you need to do here. Yep.
So the curl determines the axis that something rotates on.
As well as
the
how quickly it's doing the rotation.
Okay. Which, in that case, what direction does it turn? Like right hand rule?
I mean, by convention, I think, yeah. Right. There you go. Okay. So, well, I recognize that it's probably unsatisfying for me to define these quantities without showing you. I promise we're going to come back to this when we start studying surfaces, and the flow of vector fields through surfaces are going to be built out of these building blocks. Next time, we get to do my favorite idea in all of multivariable calculus, which is how on earth do you do a Taylor series for a function with more than one variable? Yeah, that's the good stuff. All right, I'll see you guys.